Hello everyone, I welcome you all. This is the last video on nodal analysis. In previous four videos, I had discussion on nodal analysis. In all of them, we have considered the circuits where we had only independent sources. In this video, I will consider the problems where we have the dependent sources as well in the network. So I will start with the numericals directly. The first problem is find the voltage Vx in the network shown in figure using nodal analysis. Here we have an independent voltage source. Then we have a dependent current source which is supplying 4 times I1. I1 is the current through this 1 ohm resistance. So it is a current dependent current source. Here we have 1 ohm resistance. Then 2 ohm resistance which is connected in series with 8-volt source. And across this 2 ohm resistance we have voltage Vx. So we need to find out this Vx using nodal analysis. The first step in nodal analysis is always to identify that how many nodes are there where we can apply KCL. Out of them we have to assign one as reference, and to the remaining nodes we assign the voltage with respect to reference. So here how many nodes are there? These two are the same points, since there is no potential difference when we move from this point to this point. So this is first node. This whole is one node. Means on this node we have 1 ohm resistance for a I1 current source, 1 ohm resistance, and then 2 ohm resistance. While over here, this is again interconnection of 4 elements. This is second node. Let's consider this one as reference. Assign the voltage to this node as V. So when we have dependent source in the circuit, then what we need to do, we always need to express the controlling quantity in terms of node voltage. So here what is the controlling quantity? Controlling quantity is I1. We need to express this I1 in terms of node voltage V. I1 is the current flowing through 1 ohm resistance. Its direction is marked that it's flowing in upward direction. It means it will be 0 minus this voltage minus V. So I1 will be equal to 0 minus, now what is the potential? As we negative sign came first, so it's minus 4 minus V upon 1. So it means I1 is 4 minus V. This is our first equation. Then we have to apply KCL to node. So when we apply KCL to node, 4I1 is the incoming current. I1 is the incoming current from this side. So I1 plus 4I1. We don't know the direction of current in these two branches. So let's mark them as outgoing. It should be equal to V upon 1, that is the current in this branch, plus current through this 2 ohm resistance is V minus 8 by 2. Now substituting the value of I1 in this equation, 4 minus V plus 4 into 4 minus V. This will lead to a simplified equation that 13V is equals to 48 and V is 3.692 volts. Now you need to note down over here, in this branch you can't write V minus Vx. Why? Because this Vx is the voltage drop across 2 ohm resistance. It's not the voltage source. So when we write the current, we always write the potential difference by the difference of voltages, not which we have by the sources or either the node voltages, not the voltage drops. The question was actually to find out Vx. Now Vx can be found by this we can say by applying KVL or by voltage division rule. So if we apply voltage division rule, then it will be equal to 2 into V minus 8 by 2. So V minus 8 by 2 is basically current in this branch. So that is multiplied by 2. So when we substitute the value of V, this one is minus 4.31 volts. So the application of nodal analysis was to find out the node voltage, and after that you can find out the value of Vx by any comfortable method which you want to apply. Now I'm considering another problem where we have dependent source in the circuit. Question is, use nodal analysis to determine current I in the network. Now what is the network? This one is having a current source which is current dependent current source, 3 ampere source. Here we have 4 ampere source, 10 ohm resistance, 5 ohm, 20 ohm, and current through this 5 ohm resistance is I. So first step is we need to identify that how many nodes are there. 1, 2, and 3. Let's consider this one as reference. Assign voltage to this node as V1, that is with respect to reference, and to this node as V2, again with reference to reference only. Now next step is we need to express the controlling quantity in terms of node voltages. So now what is the controlling quantity? Current I is the controlling quantity, since it is a current controlled current source or current dependent current source. So value of I in terms of node voltages is it's flowing away from node 2 towards reference. It's a current through 5 ohm resistance, so it will be potential difference divided by 5, V2 minus 0 by 5. So it's V2 by 5. Then we have to apply KCL to each node. Let's start by applying KCL to node 1. 4 ampere source is the current flowing towards node 1. So it's an incoming current. 3I is leaving. We don't know the direction of current through this 10 ohm. I am assuming this one is outgoing. Same for 20 ohm since I don't know the direction of current. So 4 ampere is incoming. This is equal to 3I. Then current through 10 ohm is potential difference divided by 10, that is V1 minus 0 by 10, plus current through this 20 ohm resistance V1 minus V2 by 20. V1 minus V2 by 20. So when we solve this, we get the equation as 3 V1 plus 11 V2 equal to 80. This is the equation after substituting the value of I as V2 by 5. So this is our first equation. You can solve the equation by your own and then confirm whether you are getting same equation or something different. Next step is we have to apply KCL to node 2. So when we apply KCL to node 2, 3 ampere is leaving this node, then current in this branch, that is current I again leaving the node, 3I is flowing towards the node, that is an incoming current. As the direction of current through 20 ohm is unknown, so let's consider this as outgoing. So current through 20 ohm resistance is V2 minus V1 by 20. Then we have 3 ampere leaving the node. V2 by 5 again leaving the node. Only 3I is flowing towards the node. So V2 minus V1 by 20 plus 3 plus V2 by 5 is equals to 3 into V2 by 5. Since the value of I we had already written as V2 by 5. So when we solve this equation, this is simplified to V1 plus 7V2 equal to 60. Now we have two equations and two unknowns, which will give us the answer of V1 as minus 10 volts, V2 as plus 10 volts, and answer for I, which is V2 by 5, is 2 amperes. So what we have seen in these two problems, that we have one additional equation for the controlling quantity in terms of node voltages. The rest of the procedure remains same as what we had applied in the previous problems where we had only independent sources. Now move on to next problem. Again, here we have to use nodal analysis. The circuit is having a 1 by 3 ohm resistance over here, 1 ohm resistance, 0.5 ohm, 3I, 0.5 ohm, 1 volt, and here we have a current dependent current source. This voltage is already given, that is Vx. Question is using nodal analysis obtain the value of Vx in the network shown. So here we have current dependent current source, and we have the special case as well. Let's identify the nodes first. Let's mark this one is first node, this one is second node, this one is a reference. Potential of this node V1, V2, they are assigned with respect to the reference. This one is already given Vx, so we need to find out this voltage Vx. Now for node 1, we have a voltage source between node 1 and reference. So this is a special case when we have a voltage source present between node and reference that will give us the answer of one of the voltages directly. So here we have V1 as 1 volt, one direct answer. Then we need to express the controlling quantity I in terms of node voltages. Now I is the current through this 0.5 ohm resistance. It's flowing away from node 2, so it means V2 minus 0 by zero point 0.5. I is V2 minus 0 by zero point 0.5. It's equal to 2 times V2. Now apply KCL to node 2. On node 2, we only know the direction of current through this 0.5 ohm, that it's flowing away from node 2. We don't know the direction of current through this 0.5 ohm. Let's mark it as outgoing, and same through this 1 by 3 ohm resistance. So current through this 0.5 ohm resistance is V2 minus Vx by zero point 0.5. Then current through this one is V2 minus 0 by zero point 0.5. Then current through 1 by 3 ohm resistance is V2 minus V1 by 1 by 3 equal to 0. Using the value of V1 as 1 volt in this, the equation will be simplified to minus 2Vx plus 7V2 equal to 3. So this is our first equation. Second equation we will get from this third node whose voltage is Vx. So next apply KCL to node 3. When we apply KCL to node 3, we know that the current 3I is flowing towards node 3, so it's an incoming current 3 into I. It should be equal to the current which is flowing away from the node through these two resistances. Now I have again marked these currents as outgoing since we don't know their direction. So current through 1 ohm resistance is Vax minus V1 by 1. Then current through this 0.5 ohm resistance, this one is Vx minus V2 by zero point 0.5. Now when we substitute the value of I as 2V2, 3 into 2V2 equals to Vx minus 1 by 1. V1 has value as 1 volts. Is Vx minus V2 by zero point 0.5. Simplification of this will lead to the second equation, that is 3Vx minus 8V2 equal to 1. This is our second equation. Now when we solve these two equations, we will get the value of Vx as 6.2 volts. And for your reference, the value of V2 is 2.2 volts. You can check your answers and verify. Now coming to the last problem where we have dependent source and the concept of supernode is also used. Question is find the voltage V2 in the network shown. The network is this is a current source, this is voltage V2, voltage across 5 ohm resistance, its polarity is already marked. This resistance has value 2.5 ohm, 2 ohm, 8 amperes, and here we have a dependent source in which polarity is marked, which means it is a voltage source. Its value is 0.8 V2. It means it is a voltage dependent voltage source. So the first step in this problem is we have to identify that how many nodes are there. 1, 2, 3. Let's assign the voltage to this one as V1, V2 and V3, considering this one as a reference. Now when this current source supplies 5 ampere current. Now when we apply KCL to node 1, we can write the current in this branch, we can write the current in this branch, but we don't know what's the current in this branch because we have a voltage source in this branch. And same is the problem faced by us when we move on to node 3. So it means node 1 and node 3 they should be combined together to make a supernode, and here the controlling quantity is voltage V2, which is same as node voltage V2. We don't need to write any separate equation for the controlling quantity. Node 1 and node 3 they are combined to form supernode. Then we have to apply KCL to supernode. So when we apply KCL to supernode, we have 5 ampere current entering node 1. We don't know what's the direction of current through 2 ohm. Let's assume it is outgoing. Then moving to node 3, 8 ampere is leaving the node 3. Since the direction of current through 2.5 ohm resistance is unknown, I am considering this one as outgoing. So 5 ampere should be equal to V1 minus V2 by 2 plus 8 plus V3 by 2.5. So this equation can be written as 0.5 V1 minus 0.5 V2 plus 0.4 V3 equal to minus 3. This is first equation. Second is the equation by constraint imposed by voltage dependent voltage source. Now what is the constraint? That V1 minus V3 should be equal to 0.8 V2. Why V1 minus V3? Because node 1 is connected to positive terminal of the voltage source. So V1 minus V3 should be equal to 0.8 V2, which will give us second equation V1 minus 0.8 V2 minus V3 equal to 0. This is our second equation. And third equation we get from node 2. So next step is apply KCL to node 2. So when we apply KCL to node 2, 8 ampere current is incoming current. Let's mark the current through this 5 ohm resistance as outgoing and through 2 ohm again outgoing. So current through 2 ohm resistance will be 2 V2 minus V1 by 2. Current through 5 ohm V2 by 5. This should be equal to 8, which is incoming current. So when we solve this equation, it becomes minus 0.5 V1 plus 0.7 V2 equal to 8. So this is our third equation. The answer of V2 is 25.91 volt, which we get after solving these three equations simultaneously. And I am giving you the answer of V1 and V3 as well for your cross reference. V1 is 20.27 volts and V3 is minus 0.46 volts. So I hope all these videos on nodal analysis will be helpful to you for your preparation. In the next video, I will start with the network theorems, specifically with superposition theorem.